Hi there. What I'm going to do today is I'm going to talk about the equilibrium constant. And this is from our second objective, our second chapter 15, which is called chemical equilibrium. Chemical equilibrium affects a lot of the things we see around us. And we are aware of it in many ways, but we don't really think much in terms of the mathematics behind equilibrium. So that's what we're going to focus on primarily is the arithmetic, the math of equilibrium. So I'm going to start by write it in here, chapter 15, chemical equilibrium, with a little picture. Okay, just a little simple little picture here for you. So imagine that we have a container, which is sometimes referred to as a vessel, like a ship. And inside this container are a bunch of particles. And let's suggest that these are some reactant. And let's give the reactant a symbol. Let's call it A. Okay. And suppose we let time go by. And what we find is that after some period of time, we don't have to worry about how long it is, that's actually kinetics. We find that there are fewer of these particles. Okay, a little bit fewer, right? Maybe put a few more in here just to really reinforce the idea that there's more of them here than there are in the second case. But interestingly enough, what we find is there's something else in there. And this other material, we'll call it product. We'll call it the product, and we'll give it a symbol. We'll call it B. Okay. And then as we continue following through time, so let's let this go for a while. So a long time. Okay. Let's say after that long period of time, we've got that many A left. And this many B. Okay. So it looks like at the end we have more B than we have A, right? Looks like there's more of those. So what we would do is we would say after some period of time, the reaction is going to become stabilized, or the term we use is it will come to equilibrium, which means that there aren't going to be any overall changes in the amounts of materials. If we were to count the amount of reactant A, and we were to count the number of product B, we would find that they're not really changing over time anymore. Okay, so it's stopped changing. So let's count up the A's. Hopefully I can count it. 1, 2, 3, 4, 5, 6. And let's count up the B's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I counted that right. What we're going to claim is that no matter how much we start off with in A or how much we start off with B, so for example, I could start off with all B's. And no A's. And what we would find is that by the time we're done, the ratio of B's by the way, let's put some more in here. Okay, I put 14 in there. To A's, okay, I would have 7 there and 14 there. See, the ratio is the same. 12 to 6 is B to A is the same as 14 is to 7, which is 2, right? And this is an interesting observation about chemical reactions. It's not always the case, but it is often the case that if you start off with starting amounts of reactants or products, either one, give it enough time to stabilize, to undergo some reaction and stabilize, you will eventually reach some point which appears to be common for that particular reaction. The ratio of the products to the reactants appear to converge to some value. In this case, it was 2, right? And that's an interesting observation. What it suggests is that 2 reactions can occur simultaneously. It suggests that we start off with A, only A. A can be converted into B over time, right? So A is going to B. But it also suggests that if we start off with B, it can over time be converted into A. Interesting, right? Both reactions can occur simultaneously. And at what we understand now is that at the molecular level, a mixture of reactants and products will undergo conversions, interconversions between each other by collisions, reactions, back and forth. So this blue one right here, this product right here, at some point it might get converted into a reactant, but then it might collide with another material and be reconverted back into product. And both of these are occurring simultaneously. We represent that by combining the 2 arrows, like so. Okay. This is often referred to as a double arrow, and it suggests that this particular reaction is reversible. Okay, the term we'll use is reversible, meaning it can go either way. Under some conditions, we can really push this reaction that direction. Under other conditions, we can push it in this direction. We can reverse the direction of the reaction. Now, some reactions are not really reversible. And in fact, when you take General Chemistry 1, usually we deal with reactions that are not really that reversible. They go to what we call completion. They're irreversible. So for example, not explosions, but burning, combustion. This one appears to pretty much only go in that direction. Okay. So if I take hydrogen gas and combine it with oxygen, I get water. It's not likely that taking a container of water, it will decompose back into hydrogen and oxygen. So the reverse reaction might be really, really, really small or not at all. Okay. So there's our double arrow. We use that to represent these types of reactions. When does this happen? It happens a lot in acid-base chemistry. It happens in biochemistry. It happens in organic chemistry. Many of the reactions that involve organic materials undergo these processes where reactions are reversible. reactant becomes product, product becomes reactant simultaneously. Again, it's called dynamic equilibrium. What a great name, dynamic equilibrium. Meaning that even though after some period of time, we reach some level where the ratio of the product to the reactant is constant, it's not changing anymore, the ratio is 2 in this case, that doesn't mean nothing is happening in there. They actually are colliding with each other, reacting with each other. In fact, if we go back to chapter 14 and consider our energy level diagram, our reaction diagram like that, this is generally written for the forward reaction. But there could be a reverse reaction. And the reverse reaction is going backwards like this, right? So that would be a reverse reaction. Okay, so for that reason, it's not uncommon to write A arrow B as forward and B arrow A as reverse. Okay, and each one has a rate constant. So the rate for the forward reaction would be K forward times the concentration of A to the X. The rate reverse would be K reverse times the concentration of B to the X. Well, I guess we would put a Y here. Okay, so we can write rate law expressions for it as well. In fact, we did that a little bit in one of the examples at the end of chapter 14. Okay, so we're going to define something called the equilibrium constant. And here I'm going to go ahead and do this kind of formally. I'm going to write out a chemical equation, which is reversible. And there are 2 reactants and 2 products. And we use this notation in chapter 14 a little earlier, where the A, the B, and the C, the D, so those are the coefficients. These are the coefficients of each reactant slash product. Okay. Now, generally, when we have a balanced equation, it could be a 1, a 2, a 3, or 4. It could also be fractions, right? It could be a half, it could be 2 halves, 3 halves, 5 halves, so forth and so on. So it's whatever it is in the balanced equation. Okay. So here's an example. It could be, for example, NO2 plus O2 goes to NO plus O3. Okay. Now everything in there is a 1. Okay, so all the coefficients are 1. But we could have another one. Here's one that's a little bit simpler. N2O4, sorry, reversible, might go to 2NO2. Okay, here the coefficient is a 2, here the coefficient is 1. We're concerned with the coefficients, and here is why. Remember when I said that the ratio of the product to the reactant was constant? That was not exactly true. It was true for that particular reaction, but the more general truth is the observation that there is a constant for reversible reactions, and I'm going to call it Kc, and it is equal to the concentration of each product multiplied together. Remember our bracket notation? Molarity, right? Moles per liter concentration. Divided by the product of the concentrations of the reactants. But we raise them to the coefficients. So CD, AB. So it's a very interesting expression. I'm going to define what this Kc is. Kc, we're going to call it the concentration equilibrium constant. Okay, the concentration, that's where the C comes from, concentration equilibrium constant. K for constant. K in chemistry is often used to represent constant. Rate constant was a lowercase k. This is uppercase K. So don't get it confused with rate constants, although they are connected to each other in certain ways. So let me write out the, for this last one down here, Kc. Here, there's only one product. So we're going to write the concentration of NO2 divided by, there's only one reactant, N2O4. So concentration of N2O4. And then there's a 2 here. So we put a 2 there. There's a 1 here. So I'm not going to put a number in the denominator, because if I just put the brackets, that means it's a 1. Okay, that's the expression. This is called an expression, kind of like a math. You know, if I say ax squared plus bx plus c equals 0, that's an expression. If I actually plug the numbers and give you the numbers, that's a calculation. This is just the general expression for what we're getting. But what it says here is that given enough time, this reaction will come to equilibrium. And when it does, the concentration of NO2 to the second power, so squared, divided by the concentration of NO2 to the first, N2O4 to the first power, will be some value, some numerical value that is a constant. Meaning, if I put in a certain amount of N2O4 and no NO2, give it enough time, the ratio of NO2 to N2O4, NO2 squared to N2O4, will be some value. If I put in all NO2, give it enough time, at some point it will reach that same value, that same ratio will be the same number it was in the first case. Doesn't matter what amounts of each reactant and product we put in, eventually it will reach that level of what we call chemical equilibrium. Okay. Now, Kc is a constant at one temperature, meaning if I change the temperature, its value may change. Okay, so it's like the rate constant. It is a constant, but that doesn't mean that I can't change that constant. The constant change is based on what the temperature is. So temperature can affect the value of Kc. All right. So that's why when you look at problems in chemical equilibrium, they will often tell you what the temperature is, not because you can calculate K based on the temperature, but because they just want you to know that everything in this problem is at the same temperature and they're not changing the temperature, because if they change the temperature, Kc might change. Okay. So there you go. So chemical equilibrium. Now let me show you just real quickly a little graph. So here's time. And then here's concentration of NO2. And here's concentration of N2O4. Okay, so what we would claim is, suppose we started off with this level of NO2. And N2O4 was essentially 0. We'll start off with right at 0. Okay, what we would say is that over time, NO2 is going to, it depends how I write the equation. So let me write out the equation here. Oh, no, we can do it this way. That's perfectly fine. Okay, so NO2 is right here. So we have some amount of this, and the N2O4 is over here. That's 0. What we would claim is that there's some value, K is some value. So there has to be a certain amount of each once it reaches equilibrium. So what will happen is the N2O4 will start to form. So it'll start going up. And then it'll kind of stabilize at some point. It won't change anymore. Whereas the NO2 it starts up here, it's going to decrease really rapidly and then stabilize as well. Okay. Now notice the NO2 kind of changed more rapidly than the N2O4 because it's a 2-to-1 ratio. We don't need to worry about that right now. But the point is that once you're out here, see how they're not changing? These are unchanging. Again, it's still dynamic equilibrium. They're still reacting with each other. It's just the ratio, the overall ratio isn't changing. What we would say is Kc would be the concentration of NO2 squared over concentration of N2O4, okay, based on that balanced equation there. So you could actually measure these concentrations, and if you could measure those concentrations, you could figure out what they are. So let me make up some numbers. Like, so for example, suppose this is 0.2 molar, and suppose this is like 0.5 molar. Okay, I'm just making up numbers here, okay? The NO2 is at 0.2, so 0.2 squared. And then the N2O4 coming up here is 0.5, right? So over 0.5. Okay. So that would be 0.04 over 0.50, which would be 0.08. So we just figured out what Kc is. All we had to do was figure out what the concentrations of these two materials are far enough out so that we know they're not changing anymore, right? You wouldn't do it here because see, they're changing. But once you get kind of like out here, they're not changing anymore. So you just measure their concentrations, plug them into this expression for Kc, and you can get the value. By the way, we're going to assume that it's unitless, that it's a value that doesn't have any units. It's a whole discussion about why that's the case. But for now, just assume that it doesn't have any units. So don't worry about plugging in units for this one. Okay. So I think at this stage, we can go ahead and start to look at a couple of problems. Just a couple. Okay. So the first one here is writing a concentration equilibrium constant expression. Well, that's an interesting title, okay? But remember, concentration, that's the little c. Equilibrium constant, that's the big K, uppercase K. Expression is just what it's equal to. Write the equilibrium constant expression for this reaction, okay? Now, I'm going to point out when you do these problems, make sure you observe the states of matter. It turns out it's important. It turns out that when we write equilibrium expressions, we need to know what, first of all, whether they're gases, whether they're aqueous, whether they're liquids, or whether they're solids. Okay. So notice these are all aqueous, okay? We don't need to worry about why right now. We'll get to that pretty soon. But right now, just get in the practice of observing the states of matter, okay? And here we go. So notice we got a balanced equation. We're just going to write the expression for it. And I always, it's a little mantra for me when I do these: products over reactants, products over reactants. That's what you think of in terms of equilibrium constant, okay? So let me go ahead and show you this particular problem. It's really quite easy, actually. So here's the balanced equation. Of course, you want it to be balanced. Otherwise, you don't know what the coefficients are. And again, I'm going to write the states of matter because we want to get in the practice of doing that. Okay, so here's how we don't have much room there, so I'm going to do it down here. Kc, you start with the first product. Remember, the coefficient is going to be in there too. So concentration CH3COO minus. Coefficient, there's a 2, so we're going to square it. Mathematically, we're squaring, not multiply by 2, square it. second product. We're going to multiply it by the concentration of the second product. First power, right? Okay. And then on the reactant side, we've got C6, H10O4. And then we've got OH minus. So times, remember, very common mistake, particularly in the denominator, people will put plus. Don't do that. It's not plus, it's multiply. Okay. By the way, this expression for the equilibrium constant, this was a big discovery by chemists. They figured this stuff out and they're like, oh, look at this. They noticed the patterns and they made measurements and they saw that this was the case. So this expression, the general idea of this expression is called the law of mass action. Okay, in other words, some of the mass is being converted from reactant to product, but under other circumstances, some of the mass of the product's being converted into reactants. So there's a mass action in this process. Okay, there's our expression for the concentration equilibrium constant. Concentration C is the subscript. Remember, use an uppercase K, not lowercase, because lowercase is rate constant in chemistry. Okay. What this says is if we knew those four concentrations, if I knew what this value was, this value, this, we could calculate our Kc. And then you're going to do that in another problem. Okay. Let's go over another one here. Same idea with this one. Okay, this, the difference here is there's no squared. There's nothing is in the second power. Notice they're all aqueous. I'm just going to scroll through another one, see if there's anything that looks any significantly different. This one looks a little different. It's got two reactants and one product. So let's do this one, okay? Notice they're all aqueous. Okay, so here's your balanced equation. Okay. All right, so Kc is concentration of products over reactants. So concentration of H2SO4 divided by concentration of the hydrogen ion, H plus squared, times the concentration of the sulfate ion, SO4 2 minus. Again, if we knew those numbers, we could calculate Kc. Okay. Simple as that. Products over reactants. It's all multiplication, division, not addition, subtraction. Don't forget the exponents. And again, pay attention to the states of matter. Train yourself to look at what the states of matter are for now. Okay, there you go. Okay. Okay, now here's one. I'm going to pop this one up. This one's kind of cool. It's a little picture, a little diagram that you have to analyze. Okay. Now there's, information down here, but let's take a look. Okay, hopefully you can see that. Recognizing equilibrium from a sketch. Okay, cartoon we call this. Tiny samples of aqueous solutions are sketched below as if under a microscope so powerful that individual molecules could be seen. And the water molecules are not shown. So these are solutes that are dissolved in the water, but they're not showing you the water because remember, if you have a solution that has water in it, there's 100 water molecules for every solute molecule. So it would just be hard to find anything except the water. Two substances in each sample can interconvert. That is, each kind of molecule can turn into the other, reversible. The equilibrium constant for the interconversion equilibrium is shown below the sketch. Decide whether each solution is at equilibrium. Okay, so it looks like there's 4 of them. Okay, so let's take a look. So for the first one here on the top left, you just have to answer whether it's at equilibrium or not. They give you the value of K, which is 4, meaning that the product concentration divided by the reactant concentration is 4. Now, there's no, remember when you write the expression, you can have a squared value in there or a cubed value in there. We're assuming here that it's just one of this turns into one of that. So the coefficients are 1. So that's why we can just say product over reactant. Okay. So we would call this the reactant and we would call this the product, but that's actually arbitrary now. It turns out it's reversible. So either one could be thought of as the reactant and the other the product. In general, we think of the one on the left as the reactant, but they're both reactants and they're both products actually. Okay, depends on the circumstances. So K is 4, they're telling us that. So what we need to know is whether we have a ratio of 4 of these for every one of those. So let's see the little tripods, right? We've got 1, 2, 3, 4 tripods. And then the little lines, the little, I want to call it like a little caterpillar. Looks like a caterpillar, right? Okay, how many of those do we have? 1, 2, 3, 4, 5, 6, 7, 8. So it looks like we've got 4 to 8, right? 4 products to 8 reactants. So that would be 4 divided by 8. Remember, it's products over reactants. That's a half. That's not equal to 4. So no, it's not at equilibrium. Let's take a look at this one. So now we've got, little pentagons versus little crosses, I guess, or plus signs maybe. Okay, so we want a ratio of 3 to 7. Okay, so keep in mind, if we're counting them, it's going to be like, if it is at equilibrium, it'll be 3 to 7 or 6 to 14 or 9 to 21, because 7 is a prime number, so you can't get many ratios that work out that way. But let's see. So the little plus signs, we have 1, 2, 3. Oh, that's so far so good. And then the little pentagons, we have 1, 2, 3, 4, 5, 6, 7. So yeah. Did I get that right? 1, 2, 3, 4, 5, 6. Yeah, so it is, that works out 3 to 7, right? There's 3 products and 7 reactants. So yes. Then we come down here for this one, K is 2 and the purple is on the product side, right? So we should have a ratio of 2 purples for every 1 green. It's not, you can tell it's not the case, right? There's 2 purples, but there's not just 1 green, right? If you have 2 purples, you got to have 1 green to make the ratio 2 to 1, which is 2. So not even close. There's way too many green ones. And then, but what can happen is the greens can convert into purple. So maybe this turns into a purple and this turns into a purple and this turns into a purple and this turns into a purple until you only have a few greens left and you have mostly purple. Once you get the ratio of 2 to 1, purple to green, then the reaction is at equilibrium. But again, they'll keep interconverting. It's just that on average, that's the value going to be. Now, these ones, they do have different shapes, like Tetris, right? If you've ever played the old game Tetris, this is one of the hard pieces in Tetris. It messes you up. Okay, so we got that one, and then we got the dark green, I guess. Light green, dark green. So it looks like the dark green is 1 for every 5 light greens. And that looks like it might be there, right? Because you got 2 of the products. If you have 10, 2 to 10 is the same as 1 to 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that one's at equilibrium. Okay, so that's just a little diagram, a little schematic to kind of show you that idea. It's kind of fun. Okay. Now, what I will do is I want to show a couple of problems from section 15.3. Okay. Because section 15.3 has a lot of problems, 3, 5, 7, 8. It's a very long section. Some of the problems are very easy, but others are a little more challenging. So what I'm going to do is I'm going to go ahead and start with section. I'm going to start section 15.3. which is called equilibrium expressions, which we just did, by the way. 15.2, we did do equilibrium expressions. But I'm just going to do part of it in this lecture, and then in the next lecture, I'll do the other half. Okay. So let's begin by considering, again, the states of matter. So remember I said before that we have Kc, and the C refers to concentration. So that's the case when the units of the concentration are molarity, right? Remember moles per liter. Okay. Well, we also have something called Kp. And this is used for gases. So P here refers to pressure of a gas. Okay, so this is used often when, or it's used only when we have gases. You can use Kc or Kp if you have a gas, but if you have a gas, you can't. But if you don't have a gas, you can't use Kp. Kp only is only valid for gases. So it's used for gases. Okay. Now, how does this work? Very simple. Again, double arrow. Kp, the only thing here is the notation. The notation is a little odd. You write the symbol P, it's uppercase, and then you put the B underneath. And that means pressure of B, okay? Then you divide that by pressure of A, and then put your coefficients in. So this would be squared, okay? And that's it right there. So if we measure the pressure of gas A and gas B, and we know those equilibrium pressures, we can calculate Kp. It turns out you can convert Kp and Kc. We'll go over that in another lecture, okay? It's just an alternate way of you know, all the kind of rules are the same as with Kc. It's just we're putting different units in. Just like Kc, we're going to assume this is unitless. Doesn't have any units, okay? And again, it's used for gases. The next thing I want to say is that if we have a solid, okay, I'm going to put aqueous there for, let's put G. Okay. This is a solid. Do not put solids into the equilibrium expressions. Okay. Again, I'm not going to go over the details of why that's the case, but we don't put the solids in there. It's an issue that we'll leave for another discussion. Okay. So that means if we were going to write K sub C, we would do concentration of B. And then what you do is if it's a solid, you just put a 1. Just put 1 in there. Okay, so divided by 1. Now, if you're dividing by 1, you can just, you know, mathematically, you can just write that as concentration of B. Okay. Let's say we had this, though. Suppose we had B gas goes to A solid. Okay. And now let's do Kp, not Kc, but Kp. Well, this is a solid, so we're not going to include it. So what do? We put a 1. And then divide that by, since it's a P, we're going to do pressure of B. Okay. So a couple issues here. Solids, you leave them out. Liquids, you leave out too, actually, but solids, you leave out. If it's Kp, if they tell you to do Kp, you could use pressure units. And then if you have a solid in there, if you feel like you need to, just put a 1 where you would put that concentration or pressure for that one. Okay. Gases, you can do Kp or Kc, but you can only do Kp with gases. So let's take a look at an example. Again, I'm just going to do a couple of these here. Okay, writing a pressure equilibrium. So pressure, Kp, not concentration, but pressure. So Kp. Hydrogen bromide, that's HBr, is a gas, and oxygen, a gas, reacts to form bromine gas and water vapor. Okay, so everything's a gas, so pressures. Write the pressure equilibrium constant expression for this reaction. The only thing that's going to be difficult about this is if you got to use the right little box, the little superscript and subscript box for Alex. Okay, that's the only issue there. Okay, so oops, let me go ahead and put this up here. For HBr plus O2 Br2 2H2O. We're gonna do KP. Products over reactants. So remember the notation is P of the first product, so that's Br2. Okay, the coefficient's a 1, that's cool. Now you can put it in parentheses just as long as it's not square brackets notation, right? So I could put it like that. Everything's a gas, so H2O, oops, sorry. Squared, right? Divided by, now we have two reactants, PHBr squared, PO2, first power. Okay, now we don't have to have the parentheses, so we could just do PBr2 times PH2O squared divided by P8. Ooh, it was a 4. I'm so sorry. That's a 4, fourth power. PHBr to the fourth times PO2. And that would work just fine. Okay. It looks to me as if you look at Alex. Oh, you know what? This is not balanced. I think I wrote the equation wrong. I'm sorry. This is 2. I'm so sorry. That's a 2. So that means I'm going to put a 2 here and a 2 there. My apologies. There's 4 bromines over here, so there should be 4 there. Okay. It looks like on Alex, they don't put the dot. They just write them next to each other. Okay. So if you run into notation problems that you can look and they'll maybe give you a little tip on how to deal with that. Okay. Okay, now that was a complicated one, right? You know, you've got something squared times something squared divided by something to the fourth divided by something to the first power. But that's essentially how it works. Okay. Okay, I'm going to show you one more here. This is called heterogeneous. So when you see the term heterogeneous, that typically means that there's more than one state of matter involved or more than one phase, we call it. So some reactions occur really cool, like a catalytic converter in the car, in the automobile, occur by having a solid surface and then gas molecules stick to the surface and they react. The metal acts as a catalyst to react the gases, and the reaction occurs on that surface. So because the metal is a solid and the gas molecules, the reactants are gases and the products are gases, that's what we would call heterogeneous chemistry. The reaction is occurring between materials that have different states of matter. In clouds, there's a lot of chemistry that happens in clouds that we don't think of. Little ice particles or little water droplets in clouds. Remember, clouds are water droplets. And those water droplets have surfaces and they have liquids on the inside, even though they're really small droplets. There's chemistry going on the surface of those droplets and on the inside. There's also little crystals, little up high enough, it's cold, so you have little ice crystals up there too. Chemistry is occurring on that surface. That's heterogeneous because you have a solid and a liquid reacting with gases. So we often see this occur. It turns out, just like solids, liquids do not appear in the equilibrium expressions. So solids and liquids, omit them from the equilibrium expressions, just put a 1 in for them, okay? So here's an example. CH3, CO2, C2H5. I guess this is methyl ethyl acetate, is reacting with water to form acetic acid and ethanol, okay? So notice, like I said earlier, get in the habit of looking at the states of matter. Aqueous, liquid, aqueous, aqueous. The liquid is just going to be a 1, okay? Write the concentration equilibrium expression. That's all we have to do for that one, okay? So remember, if you have a solid or a liquid, you omit them from the equilibrium expression. Okay, so other than that, it's pretty easy. So, they pick some big molecules here. So you have to write these all out. Okay, so it says concentration. It didn't say well, obviously we can't do pressure because these are not gases. So just products over reactants. So the first product is aqueous. The second product is aqueous. Everything's a 1. All the coefficients are 1s. Okay, now typically if you have something else in, the divisor, you can just take the 1 out. You don't need to have the 1 in there. Technically, it's not incorrect, but there's no need to have it in there, okay? So this would be our equilibrium expression, concentration equilibrium expression for that particular reaction, okay? And there you go. So that is, the beginning of section 15.3. So I just did section 15.2, and then I started on 15.3, but there are, like I said, there's a bunch of problems in 15.3. So the next video will cover some of the problems from 15.3, and then later on we'll get into 15.4 and 15.5. Okay. So thank you and take care.